Hi everyone, I'm Dan Fullerton, and today I want to talk to you about the electric potential due to continuous charge distributions. Our objectives are going to be to calculate the electric potential due to the following continuous charge distributions: a uniformly charged ring, a uniformly charged disk, a spherical shell of charge, and finally a uniformly charged solid insulating sphere. So let's dive right in. Our first question: find the electric potential on the axis of a uniformly charged ring of radius r and total charge q at some point P located at a distance z from the center of the ring. Well, our strategy here is going to be to add up all the little potentials from little pieces of charge as we go all the way around the ring. So the potential at point P is going to be the sum over all I for all of those little potentials due to the charge I, which is going to be 1 over 4 pi epsilon 0 times the sum over all I of qi divided by ri, where ri is just going to be the distance from that ring to our point ri. All right, this implies then that the potential must be equal to 1 over 4 pi epsilon 0, and we're going to break these little pieces of charge up into such small pieces, then we're going to add up all of the potential due to each of those little pieces. We're going to sum them all up. So that's going to be the integral of, well, instead of our total qi, that's going to be dq. And instead of Ri, well, notice everywhere that Ri is just going to be R. So dq over R, which implies then that the potential at point P must be equal to 1 over 4 pi epsilon naught. Anywhere around the ring, Ri is the same. You're the same distance from point P, so that's a constant. Integral of dq. Well, what else do we know? Ri over here, if we make a right triangle out of it, we have one side here, and our other side here, whose distance is r, there's z. So we've got a right triangle. We could say that Ri is equal to the square root of z squared plus capital R squared. And of course, the integral of dq is just going to be our total charge q. So that's going to tell us then that our potential at point P must be equal to capital Q over 4 pi epsilon naught times 1 over Ri, which is the square root of z squared plus r squared. The potential at point P due to a uniformly charged ring. Let's take a look at the electric potential due to a uniformly charged disk. Find the electric potential on the axis of a charged disk of radius r and total charge q again at point P located some distance z from the center of the ring. So it looks a lot like our last setup. Our strategy here, now that we know what the potential is due to a ring, is going to be to go from 0 to r as we add up all the slowly increasing rings of charge until we get the entire potential. So, as we do this, let's set this up again. We're going to call dq now is going to be the charge in each little ring, dq, the width of which is dr, as we integrate from little r equals 0 to capital R to get our entire disk. The charge of that ring is dq, and we also have the distance from that ring to point P, which we'll call Ri, which, just like our last problem, is going to be the square root of z squared plus, well, we better make this one little r squared, because now we're defining capital R as the total radius. So from z squared to r squared, whatever our r is as it goes from 0 to capital R. All right, if we do this, let's start off by talking about the surface charge density. Sigma must be the total charge divided by the area, and the area of our disk is pi capital R squared Therefore, the little bit of charge dq is going to be, well, dq is going to be that ring times the surface charge density, the area of that ring, which if we cut it and spread it out, it would have dimensions of 2 pi r, its length, times its width, dr, and then times the surface charge density, sigma, which then tells us then, if we put that all together, that dq must be equal to 2 pi r dr times sigma, which is capital Q, over pi capital R squared. We're going to need that here pretty soon. All right, a little bit longer derivation here. Once again, our total potential, V at point P, is going to be the sum over all I of our individual potentials I, which is going to be 1 over 4 pi epsilon 0, sum over all I of our dq's over Ri. Or potential at point P is going to be 1 over 4 pi epsilon 0 integral from our variable r equals 0 to capital R, the total radius of our disk, of dq we just defined as 2 pi r dr capital Q over pi capital R squared Ri. All right, we've done the physics. The rest of this is just a math problem. It might take us a little bit to get this integral, but we've already done the physics here. Everything else, just math. Okay, so let's see if we can't simplify this and get VP into a little bit more reasonable form. First thing I'm going to do is pull out all of the constants that I can. So I'm going to come down here and write that VP must equal 2Q over 4 pi epsilon naught capital R squared integral from 0 to R, capital R, of R dr over Ri. Just pulling out all of the constants, our 2, our pi, our q, our pi, and our capital R squared. All right, if that's the case, then we also know Ri again is z squared plus little r squared. So that's going to imply then that VP equals, well, 2 over 4, that's just going to be 1 over 2. So that's going to be Q over 2 pi epsilon 0 capital R squared integral from 0 to capital R of z squared plus r squared to the negative 1/2 r dr. Well, I want this to fit the form u du, u to the negative 1/2 du. So if this is my du is going to be 2r dr, which means I've got to put a 1/2 over here, so I'm really just multiplying by 1. Once I do that then, if my u is z squared plus r squared, then my du is 2r dr, then I'm just integrating u to the negative 1/2 du. That I know how to do. So that implies then that VP must equal Q over, well now we've got 4 pi epsilon naught capital R squared, and we also have our what we get when we integrate here, 2 z squared plus r squared to the positive 1/2 evaluated from 0 to capital R. That's easy enough to evaluate, so I can write this now as VP equals Q over 2 pi epsilon naught, 2 in the numerator, 4 in the denominator, going to leave the 2 down there, 2 pi epsilon naught r squared times the quantity of z squared plus r squared square root minus z. All right. Let's move on. Here we have the electric potential due to a spherical shell of charge. So it's hollow. We want to find the electric potential both inside and outside this uniformly charged shell. Its radius is capital R and it has a total charge, capital Q. Follow the same basic process, process that we have been, except now I'm going to take the fact that I know the electric field. And we're going to start with the potential outside. So I could write that the electric potential outside that sphere is the opposite of the integral of E dot dl. Just taking another path here to show you how it's done. That's going to be the opposite of the integral, and we're going to go from r equals infinity, long ways away, all the way to some radius r, of, well, the electric field, 1 over 4 pi epsilon naught q over r squared dr. Electric field due to that hollow shell of, due to that spherical shell of charge should be pretty familiar by now. I can pull out my constants again, so that's going to be minus q over 4 pi epsilon 0 integral from r equals infinity to r of r to the negative 2 dr. This implies then that the voltage outside, the potential, is just going to be minus q over 4 pi epsilon 0. Integral of r to the negative 2 is going to be minus 1 over r, evaluated from infinity to r. That's just going to be 1 over r minus 1 over infinity, or 1 over r. So what I'm going to come up with is that the potential outside that sphere must be equal to q over 4 pi epsilon 0 r. All right, but how about inside? Well, let's take the same path. The potential inside is also the opposite of the integral of E dot dl, which in this case is going to be minus the integral from infinity to capital R. So we're going to integrate from a long ways away up until we get to capital R, the radius of the shell, of 1 over 4 pi epsilon naught q over r squared dr. That should be extremely familiar now. And then we also have to take the rest of the distance from capital R to wherever r is. So we went from infinity to r, capital R. Now we've got to do the next step from capital R to whatever point, whatever radius we're talking about specifically inside the sphere. So we've got to take this piecewise, do each piece from infinity to capital R and from capital R to whatever radius we're going to stop at. So that will also be minus the integral from capital R now to little r of the electric field inside a hollow sphere, 0 because there's no enclosed charge, dr. We've already done this, so that's just going to be q over 4 pi epsilon naught capital R. So if I were to graph something like this, let's put the potential on the y. We'll put r on the x-axis. We're going to end up with something that inside capital R is a constant, where this is equal to q over 4 pi epsilon naught r. And once we get to that radius, now we're going to have a 1 over r relationship where our potential is q over 4 pi epsilon naught, our variable r. All right, let's see if we can't do just one more. Find the electric field and electric potential inside a uniformly charged, solid insulating sphere of radius r and total charge q. Well, if this is a solid sphere, what we're going to start off with is taking a look at the volume charge density. Volume charge density, rho, is going to be total charge over the volume, which is going to be q over the volume of a sphere, 4/3 pi r cubed. Or we could say that rho then is going to be 3q over 4 pi r cubed. There's our volume charge density. All right, now that we've got that, let's talk about a strategy. Let's see if we can't first find the electric field. We'll choose a sphere as our Gaussian surface. So the integral over the closed surface of E dot dA equals our enclosed charge divided by epsilon 0. The left-hand side, because we've chosen a symmetrical shape and we have uniform charge, the electric field is symmetric, so that's a constant anywhere at that radius. The left-hand side is going to be E. That comes out, and the integral over the closed surface of dA is just the area. So the area of a sphere, 4 pi r squared, must equal the charge enclosed. Well, that's going to be the volume charge density times the volume of our sphere divided by epsilon 0. All right, when we do this, we just found that rho is 3q over 4 pi capital R cubed. We've got an epsilon naught in the denominator, and our volume of our Gaussian sphere must be 4/3 pi r cubed. So we've got a 3 down here as well. With some simplifications, we can get rid of our pi's. We've got some 4's. We've got some 3's. So I come up with E times 4 pi r squared must equal Q over epsilon naught r cubed over capital R cubed. But we want just the electric field. So let's divide both sides by 4 pi r squared to find out that the electric field then must be, if we divide that by 4 pi r squared, I'm going to get Q over 4 pi epsilon 0 capital R cubed times our variable r. There's our electric field. Next, we can integrate to find the electric potential. Note that since our total integration from infinity to r must be done piecewise because our electric field is going to be discontinuous. So our potential V is minus the integral of E dot dl, or in this case, E dot dr. So that will be from infinity to r of E dot dr. And if we do that piecewise, that implies that our potential is going to be minus the integral from infinity to capital R of E dot dr minus the integral from capital R to our final radius r of E dot dr inside the sphere. So that's going to be minus the integral from infinity to capital R of 1 over 4 pi epsilon 0 capital Q over r squared dr minus the integral from capital R to r of 1 over 4 pi epsilon 0 capital R cubed r dr, our electric field inside that sphere. All right, let's take our next step. This implies then that our potential is going to be equal to, well, that's just going to be Q over 4 pi epsilon 0 capital R. We've done that a few times already. Minus, let's pull out our constants. We'll have Q, capital Q, over 4 pi epsilon, oops, I forgot my Q over here. 4 pi epsilon naught capital R cubed, integral from capital R to R of r dr. Integral of that's just going to be r squared over 2. So I'm going to get, left-hand side, Q over 4 pi epsilon naught capital R minus Q over 4 pi epsilon naught capital R cubed, and we'll have r squared over 2 minus capital R squared over 2. Now just a little bit of algebraic simplification. That's going to be Q over 4 pi epsilon naught capital R minus Q, little r squared over 8 pi epsilon naught capital R cubed plus q capital R squared over 8 pi epsilon naught capital R cubed. Which implies then, with a little bit of simplification, that our potential is going to be 3q over 8 pi epsilon naught capital R minus q little r squared over 8 pi epsilon naught capital R cubed. Or let's do one more simplification step to say that the potential then must be q over, we'll factor out that 8 pi epsilon naught capital R times 3 minus little r squared over capital R squared. So a couple different ways we can do this. Hopefully that gets you started with finding the electric potential due to continuous charge distributions. Thanks so much for your time and have a great day.